Welcome. Today we're going to talk about rates of change. Hopefully you've heard that the rate of change is the derivative already. Now, there are many names for this. The slope of the tangent line, the instantaneous rate of change. There are also such things as average rates of change, but I'm not going to talk about them today. But an average rate of change would be the slope of a secant line. Maybe we'll talk about it a little, but probably not. What I really want to do is, though, talk about where rates of change happen when it's not changing time, it's changing something else. So we're going to talk about the concept, kind of develop the idea, and then maybe give a couple examples to help illustrate what I'm talking about. So the concept. Let's take a function, f of x equals x squared plus x. Well, that is a function. We could also think of it as the output, the y is equal to x squared plus x. So if I want to take the derivative, I might write it as f prime. Well, what is that? It's 2x plus 1. Or I could say y prime equals 2x plus 1. But that doesn't really get to the heart of what's going on. The prime means the derivative. And it actually comes from Newtonian calculus. Newton considered all functions things that could change with respect to time. If you've ever had a physics class, you'll notice the dot there is a derivative with respect to time. And the derivative is, with a prime, the same kind of notation. It's the same idea. But Leibniz had a different way of writing derivatives. He would write df dx, or more precisely, dy dx is what we want. This is sort of how we're talking about it. The derivative of y with respect to x. This notation allows us to have a more complicated formula that has more than one letter in it, take a derivative, and know what we're talking about. So let's give an example of what I mean. So, for a cylinder, this is my drawing of a cylinder. It's got a height h, it's got a radius r. The volume, as you hopefully know, is pi r squared times h. Now, if I modify r or I modify h, the volume will change. So imagine, I get the radius bigger. There's more volume. Or I shrink the height. There's less volume. But as I shrink that height, how fast is the volume changing? That's a rate of change. So I can talk about the rate of change of the volume with respect to height. So in writing this notation, notice the volume's not changing with time. Or maybe it is. Maybe the height is changing with time, but we don't care. We want to know how the volume is changing as the height changes. So h is our variable. If h is the variable, this is a constant. So we have a constant times h. We've done enough derivatives already that when you have a constant times your variable, the derivative is just that constant. What about with respect, however, to the radius? Is that the same thing? If I shrink the radius, is it shrinking linearly? Is it shrinking what? This constant means a constant change. So it's, as I shrink the h, it's changing at a constant rate, the same amount per change. But what about with r? As r changes, r is now our variable. Pi and h are constants. The derivative of r squared is 2r. There's nothing magical about that, it's just a different letter. If I put it together carefully, I get 2 pi r h. Now, if I start shrinking the r in, when r is big, this is more of a change in volume. Eventually there's not much, and so it changes slower. Conversely, think about it. As I expand r, going outward, it grows. But it grows more here, it grows more here. It's growing faster. The volume is growing faster as r gets bigger and bigger because r is in here. This is no longer a constant rate of change. Let's go on to talk about another example, gravity. Newton, while I may disagree with his notation in this particular example, did a lot of things working on gravity. So his force of gravity was some universal constant g times the mass of the first object times the mass of the second object divided by r squared. So here's our object system. The force of gravity pulls m2 in towards m1 based on that force. Now, if you shrink r, what's going to happen to f? As r gets smaller, what happens to f? That's a good question. So I want to know what is the derivative of f with respect to r. R is our variable. So, well, these are all constant. They're not our variable. They're a number. They're a number that's written in a strange way. So I have a number over r squared. Or, another way of writing that, number times r to the minus 2 power. So if I take the derivative should be bringing the minus 2 out. And then the number, which is all this stuff on top here, times r to 1 lowered power. In this case, it'll be divided by r cubed. As r shrinks and gets smaller, this stays negative and goes in and gets larger and larger. So the closer you are to the object, the more force inward you have. What about with respect to mass? If your mass starts shrinking, I don't know exactly how that would happen, but you've got a balloon and the air is being released or whatever, then as the mass starts shrinking or growing, how does this change? Well, let's take a look. M2 is our variable. These are all constants. We have a constant times our variable. It's very much like the previous one with height. It's a number times the variable. The derivative of that will just be the number. So, in terms of our variable, this is constant rate of change. Well, how do you interpret these? What do they mean? That's a good question. And it's a question for the application rather than the calculus. But hopefully you can see the derivative of f with respect to r is very different than the derivative of f with respect to the second m. You could also take the derivative with respect to m1, and hopefully you can figure out what that is. You can't really take the derivative with respect to g because it's supposed to be a constant, and constants can't change. But maybe they'll discover something new in physics that actually does change over time, or something. I don't know. If you have any more questions, try some out. Until next time, this is Dr.